Hello, and in this chapter, we're gonna now be looking at collisions in 2 dimensions, okay? So this is gonna be where things move at an angle. So as you can see in this diagram here, we've got things involving angles, okay? So that creates 2 different dimensions. We've got vertically and horizontally, so up and down and left and right, okay? So we're gonna be extending our work with 1D collisions into now 2D. Okay, and so here we are, and as a reminder, this is going to be for year 13 only, or the full A level. So if you're only doing the AS version, you don't need to worry about this topic here. But there we are. So let's have a look at this then. So as I said, it's moving at an angle. So what's happening here in this diagram is we've got this little ball here, right? And it moves towards this floor, okay? This floor here, the ground, and it's moving with speed u, okay? It's moving with this sort of vector, right? It's moving to the, it's going to move to the floor with that speed there, okay? And it hits the floor at an angle alpha. Okay, and then after it's going to bounce off the floor, then it rebounds off the floor with this speed v. Okay, it's going to change speed as it hits the floor, and that's going to leave with an angle beta. Okay, so the idea is before the collision it hits the floor at an angle alpha, then afterwards it bounces off the floor at a speed at an angle beta, and so that creates different speeds, right? Now, the idea is, it's kind of like with forces, we can kind of split up the speeds vertically and horizontally, okay, as that will make our life a lot easier. So, obviously we've got this sort of vector u, right, my speed or velocity going in this particular way. Well, actually, if I say do this, well, actually, if we want to go down, if we want to go in this direction, we can alternatively say we go straight down like this and then across like this. And that gets me the exact same sort of direction, right? Hopefully happy with that. Very, very, very similar to resolving forces at an angle, which we've seen before, right? And so if we look at this little triangle here, okay, so remember we've got this little triangle here. Well, hopefully you can see that this is going to be u sine alpha, right? Remember sine, usually it's opposite the angle, right? And then this component's going to be u cos alpha, okay? So u sine alpha is my vertical part and u cos alpha is my horizontal part. Hopefully happy with that, right? So that's just from the little triangle here involving u and alpha, okay? Just using a bit of a SOHCAHTOA, right? And so we split up the speed in this way. That's what we're going to be wanting to be doing all the time with these, with every question, is splitting up horizontally and vertically like this. We can then do the exact same thing for the speed afterwards. So if I do this in a different color, okay, well, it now bounces off the floor with this different speed v going in this direction. So again, I can split up this direction in this way, so I could go straight across and then upwards, okay? And so actually I should probably do it different color. I'm not sure, it might be a bit hard to read, my apologies. Okay, so if I do it in purple, okay, so I can go straight across and straight up, and that achieves the same direction. Okay, so I'm splitting it horizontally and vertically, right? So again, this is going to be v cos beta, and this is going to be v sine beta. Okay, again, in the same sort of way, right? So that's generally the idea. We want to split up these speeds or velocities in this sort of way. Okay, now it turns out that now we can consider this as perpendicular and parallel to the floor. So obviously look at these two. Firstly, these two, they're across the floor, right? They're horizontally, they're going across the floor, they're parallel to the floor. Okay, so these are my parallel components, okay, because it's going along the floor. And so then these two components going upwards and downwards vertically are my perpendicular components, because they're going to be at right angles to the floor, right? Right angles to the floor, right? So we can basically classify this as parallel and perpendicular components, okay? And so why do I bother emphasizing that? Well, it turns out that actually when it's parallel, the components are not changed. Which means, what do I mean by that? Well, it means if this is my if that's my parallel component, u cos alpha before the collision, and this is my parallel component after the collision, they're unchanged, so they're still equal. Which means we can say that u cos alpha is going to be v cos beta, okay? And that's one equation we can use, okay? So that's the idea, is that the parallel parts, okay, that's across the floor, are the same before and after, okay? What about perpendicular? Well, actually, it turns out perpendicular, well, it does change, okay? So this is my perpendicular component before the collision, this u sine alpha, and the perpendicular component afterwards is here. It turns out they do change, but specifically due to the coefficient of restitution, right? So the coefficient of restitution only affects the perpendicular components, okay? So I'm going to say for the perpendicular parts, the components are changed by E. And so if you remember from chapter 4, that essentially we saw that E was the speed afterwards divided by the speed before, right? So that means, well, the speed afterwards, well, the perpendicular part is v sine beta. So v sine beta, that's going to equal, then if I divide it by the component before the collision, so the perpendicular part is u sine alpha, right? That's going to equal E. And actually, we can then just times across to say that v sine beta is eu sine alpha, okay? And that's my second equation, okay? So if I now rewrite this first one here, just to bring it down here, we're going to be using these two equations all the time, okay, in this section, okay? So this is sort of the derivation, the idea behind these equations, right? It's kind of like how in the chapter 4, when we looked at 1D collisions, we always use momentum and restitution to get two equations, simultaneous equations. It's the exact same idea here, but these are the two equations we're going to get in this scenario here, okay? So there we are, okay? And so that's for all my speed. So I'm going to get rid of all this now, okay? What we can also look at is impulse, okay? So you can see impulse is included here. Now, again, impulse is always perpendicular to the surface, okay? I'll make a note of it here. So, in this case, so if this is my impulse, then hopefully you can see that, right? The impulse, it's at a right angle here, okay? It's at a right angle to the surface. Hopefully you can see that, right? And so that's the idea, okay? So we will be utilizing that as well. But there we are, okay? And lastly, I just want to briefly talk about something called the angle of deflection, okay? Now, this is my direction before the collision, right, between the wall. If I extend this, okay, this original direction like this, right, hopefully happy with this. Well, the angle deflection tells me the angle at which the direction has been changed, at which it's been turned around. So if we want to go from U to V, it's going to be this angle here, right? And so that's my angle of deflection. It's the how much it's been deflected by, how much it's been changed by, right? So that's the idea, right? So that's my angle to go from U to V. So it's going to be this whole angle here. Well, actually, we got one part of it, beta, already. Well, what about this angle then here? I'll call this theta. How do I find theta then to find the angle deflection? Well, to work that out, what I'm going to do is just consider the I'm going to do this diagram here. Where should I do it? I'll do it here. All right, I'm just going to consider the initial speed, okay, and then the wall. So we've got the wall here, then I've got my initial speed, right, and then I'm continuing it on like this. So this is alpha, right? So this is U, that's my wall. So I've just copied the diagram out for U, for the initial speed U and the wall, okay? But we want this angle here, theta. Hopefully you can spot that we've got vertically opposite angles, right? If we look again, look at this diagram I've got here, alpha and theta, these two angles are marked, are vertically opposite angles. Remember, vertically opposite angles from G to C, basically when you make a cross, right, when two lines cross over, the sort of the vertically opposite sides are equal. So if this is X, this is also X, right? This is Y, that's also Y. Vertically opposite angles are equal, which means that theta here is also alpha, because they're vertically opposite, okay? Hopefully happy with that, which means that theta is also alpha. So therefore the angle deflection is just alpha plus beta, okay? And so there we are. So we can easily calculate the angle deflection like this, okay? But as I said, it's generally just a very good idea to just extend the direction to help you clearly see the angle you're working with, okay? But there we are, okay? And the last comment I'm going to make is that this angle here, by the way, that angle is not the angle deflection. So this whole angle theta here, that's not the angle deflection. The textbook doesn't really explain it very well. It's quite a bit misleading, but that's not the angle deflection, because this angle is actually 180, take away alpha, take away beta, because obviously these are angles on the line, right? So they have to add up to 180. So that is not the angle deflection, okay? This is the angle deflection there, okay? So to help you visualize where the angle deflection is, you should extend the velocity, and then you can see it in the way we've done it there, okay? But I want to clarify very clearly that this angle is not the angle deflection, okay? So if you're confused about that, that's not what that means, okay? Okay, so we've got this question here first. I actually made this question. I think it was a good idea to just make a question that breaks the process down before we look at a full-on question, right? But let's have a look at this. So we're told a smooth sphere collides with smooth horizontal floor, but we've also I've given you a diagram here, right? So we've got this sphere that hits the floor. Before the collision, the sphere moves with speed 6, then rebounds with speed v, and then it's giving me some angles, okay? All of this is in the diagram, right? So I don't really need to say that. Also, E is a third here, the coefficient of restitution, okay? I'll make a note of that. So it says, firstly, by considering the parallel and perpendicular components for the speeds, we need to get these two equations here, okay? So remember, we mentioned that we should get these two equations here, okay? Always, right? These two equations. So let's have a look at it here. So, firstly, again, if I split up the speeds, so this is, so before, right? This is going to be 6 sine 60, and this is going to be 6 cos 60. Okay, hopefully happy with how I split up this speed 6 here, horizontally and vertically, right? Then I can do the same afterwards. So if I have speed v here, well, if I go across like this and then up like this, and v sine theta. Right, hopefully happy with how I split up the two speeds in this way, right? So then if we firstly think parallel, so parallel to the floor or the surface, right? The parallel components are 6 cos 60 and v cos theta. They're equal because remember parallel parts are equal. So 6 cos 60 is v cos theta. Therefore v cos theta, we can actually just put this in the calculator and you should get 3. Okay, well that's the first equation they wanted. V cos theta is 3. Great. Then I'm going to do the same for perpendicular. So now perpendicular, well, the perpendicular part, v sine theta, okay, is going to be e lots of the speed before. Now the perpendicular part before is 6 sine 60. And so then we can simplify all this. So v sine theta is going to be e, which was a third, times 6 sine 60. If we work that out, you should get 3 root 3. And so you just get v sine theta to be root 3. And that's my second equation there. And so we got the two equations they wanted. Okay, so hopefully happy with that. Okay. So then we now need to solve these effectively to find v and theta. Okay, so if I bring this, if I bring these two here, okay, right, now we're going to solve them simultaneously. Now for the first part, they said, hence, by first squaring the equations, find v. So we need to square them first, okay? And we're going to always want to do this, okay? So if I square that, so if I call this equation 1 and 2, so 1 squared, firstly, if I square the first equation, it's going to be v squared cos squared theta is 9. Hopefully happy with that. Then if I also square the second equation, I'm going to get v squared sine squared theta is 3. And there we are. Okay, now, okay, so if I call this equation 3 and 4, well actually, hopefully there's a certain trig identity that is screaming here. Okay. If I now add these equations together, I will get v squared cos squared theta and v squared sine squared theta is 9 add 3, which is 12. Okay, hopefully happy with this. I've just added the two squared equations like this. Well, actually, I can also factor a v squared out. And hopefully it's a lot more apparent what we can do here now, right? What can I do here? Well, think back to year 1, normal maths, a trig identity. Sine squared and cos squared is 1, isn't it? So that just gets me v squared is 1. Oh no, sorry, 12 equals 12. Okay. So v squared on its own is equal to 12. Hopefully happy with that, because remember, sine squared and cos squared is always 1. That's a trig identity you need to know, right? So v squared is 12, therefore v is going to be root 12. Okay, or that simplifies to 2 root 3. And that is my speed v. So we found v. Okay, hopefully happy with that. So that's the idea. We want to firstly square the equations. Then to find theta, it now wants us to divide the two equations. Okay, in this case here. So if I rewrite this again, right? So I have v cos theta is 3 and v sine theta is root 3. Well, actually, we know what v is. We could just sub in v, and then you can find theta that way. But especially when there's algebra, it's not going to be as easy. It's not going to be easy to do that really. But a very good trick we can do by dividing these two equations. Okay, so if this is equation 1 and 2, which one are we going to divide by which? Well, hopefully there's another trig identity that you might be remembering. Because we know that sine squared and cos squared is 1. What's another one we know? Maybe one involving tan, right? So if I do the second one divided by the first one, it's going to be v sine theta over v cos theta is root 3 divided by 3. Now what's beautiful here is the v's go away, so I don't need v here. So I just get sine theta over cos theta is root 3 over 3. Well, actually, what does this simplify to? Again, another trig identity, sine over cos is always tan. So therefore, tan theta is root 3 over 3. And now it's a lot easier to solve with just theta, okay? So therefore, theta, if I just do inverse of that now, inverse tan of root 3 over 3, I get the angle 30 degrees, okay? And there we are. So that's my angle there, okay? Now part B is asking to work out the impulse exerted on the sphere by the floor. Now remember what we also discussed was impulse is perpendicular to the surface. So the impulse is going to act straight up like this, okay? And that's going to be perpendicular to the surface like that, right? Now, so impulse, again, think back to earlier in the course, impulse is mv take away mu, right? But the issue is, what are the speeds we're considering here? What's v and u? Now, actually, it's not going to be just v and 6, okay? So v, by the way, was root 3. So if I just call this root 3, so the speeds for the impulse are not going to be root 3 and 6, okay? Why? Because they're not perpendicular. But what is perpendicular? What speeds are perpendicular? It's going to be these speeds vertically, right? So it's going to be 6 sine 60 here, and 6 and then root 3 sine theta here, okay? So for the if I want to work out the impulse, because impulse acts perpendicular, therefore I need the perpendicular speeds, okay? So I do not consider just the speed 6 here. I need the vertical part. I need the perpendicular part. So impulse is going to be m lots of well, for v, so my final speed that's perpendicular is root 3 sine theta. Take away m, lots of u. Now u, the perpendicular part is 6 sine 60. Okay, so I'm just considering the perpendicular speeds because impulse is perpendicular. Now for this speed as well, remember directions matter. Impulse is acting upwards, so is the final speed. But then this speed before is acting downwards. So it's going to be the negative direction. So we actually need to negate this, okay? So what we get left with is I is m lots of root 3 sine theta. Plus, by the way, we know that sine theta is 30. Sine theta is 30, so we can add that on, right? Plus 6 sine 60, okay? So that simplifies to m lots of, if we chuck all that in the calculator then, root 3 sine 30, add 6 sine 60, we get 7 root 3 over 2. And there we are. Now, I didn't include the mass. My apologies. Let's just say the mass is 1. Okay, let's keep it very simple. Actually, no, I'm going to call it 2. Okay, let's say the mass is 2. So 2 lots of 7 root 3 over 2, which just goes to 7 root 3. And that is my impulse. Okay, there we are. So that's the key idea. Remember, impulse is perpendicular, so we need to consider the perpendicular speeds when we use the impulse formula. Okay, but hopefully happy with that, okay? And also pay attention to the directions. Upwards we're going to take as positive, and then downwards is like the negative direction. So we need to negate the negative, the speed going downwards, okay? But there we are. Okay, then in part C, it wants me to find the angle deflection, okay? So if I get rid of all this again, so remember the angle deflection is how much the direction is changing by, the angle it's been changed by. So again, to really help see this, let me extend this initial speed here, okay? And also remember that this angle between here and the wall and the floor, sorry, is also 60. It matches this, okay? Remember, they're vertically opposite angles. So this angle is 60 here. And so therefore, the whole angle deflection here is just going to be 60 add theta. Okay? But remember, theta is 30. So we just get, actually, it's 90 degrees, okay? The angle deflection is 90 degrees there. That's how much the direction is being turned by after it bounces off the wall, off the floor, sorry. But there we are. And now we've got this question here. So it's a lot less structured, right? But it's going to be the same sort of thing. So here we're told a smooth sphere S is moving on a smooth horizontal plane with speed u when it collides with a smooth fixed vertical wall. At the instant of collision, the direction of motion makes an angle 60 with the wall. Coefficient restitution is a quarter. And so it wants me to find the angle, to find the speed after the collision. Okay, so of course we're going to want to draw a diagram. So what's happening here? Now actually we're told it hits a vertical wall. So it's not going to be a horizontal surface, it's going to be a vertical one. So it's going to be a vertical wall like that. Okay, something like that, right? If I can make it straight as I can, but there we are. So we're told that it's going to hit the wall with speed u. Okay, so it's going to go towards the wall like this. Okay, with speed u. Okay. And the angle it makes with the wall is 60. So this angle before it hits the wall is 60 degrees there. And then it's going to rebound off the wall. Okay, let's say it rebounds like this. Okay, so it has a speed afterwards of v, and then also an angle I'm going to call, let's say, beta. Okay, so there we are. So that again, that's the main idea, is that we have a speed and an angle. Okay, it makes with the surface. Right, so we're going to apply our usual stuff. So remember that firstly, the parallel part, again, if I was to split this up, okay, so this is going to be u sine 60, and this is going to be u cos 60. And then afterwards, again, we're going to have v cos beta, and then upwards of v sine beta. So I'm literally just splitting up the speeds into vertical and horizontal parts like that. Okay, so firstly the parallel parts, that go along the wall, well, this part goes along the wall, right? U cos 60, that's going to equal the other part afterwards of v cos beta here. Okay, and that's my first equation. Then I can also say the same for the perpendicular part, but then we need to factor in E as well. So perpendicular, well, V sine beta, okay, is going to be E, lots of the original speed, U sine 60. So U sine 60 here, and there we are. So if I just simplify these equations now, at this point it's just algebra, right? So we've got the two equations, okay, there we are. So, that means that v cos beta, well, v cos beta is going to be u cos 60, but cos 60 is a half, so it's going to be half u, and that's my first equation. Likewise, v sine beta is going to be e, which was a quarter, right? So it's going to be a quarter times u sine 60, which is going to be root 3 over 2. Actually, I'll do it here. Let me break it down. So it's going to be a quarter times u times sine 60, which is root 3 over 2. That will simplify to root 3 over 8 lots of u. Okay, so there we are. Hopefully happy with that. So root 3 over 8u here. And there we are. Okay, so now I've got these two equations. Again, I'm going to solve them. Now, in this particular way, because we've got a trig involved, the way we want to solve this is firstly, let's say we square them. So if I add the squared part, the squared equation, sorry. So if I square each equation and add them, I'm going to get v squared cos squared beta. Cos squared beta. Add v squared sine squared beta. It's going to be a half u all squared, add root 3 over 8u all squared. Now it's a bit of algebra here. It's going to be a bit fiddly, but literally don't panic about it. Let's just do it step by step. Well, firstly, I can factor out a v squared quite nicely. And so then if I simplify the right side, so if I collect the u's, I'm going to get a quarter u squared, add hang on, I get 19 over 64 u squared. Okay, if I simplify all of that, okay, make sure you're happy with that. But there we are. Well, actually, again, this just goes to 1, right? So then we just left with v squared is just 19 over 64 u squared. Therefore, if I root that, I get v to be root 19 over 8 lots of u. Okay, again, it's just going to be in terms of u, but that's my expression for the speed afterwards. Okay, and there we are. Okay, so that's v, but then I want so that's part A done. Okay, that's the speed. Okay, now I'm going to need to find beta. Okay, the angle beta. So now I'm going to divide the two equations instead. Now again, I want to do the second one divided by the first one because I want to do sine divided by cos. So if I divide the first one by the second one by the first one, sorry. So that's going to get me v sine beta over v cos beta. And so that's going to be root 3 over 8u divided by a half u. Okay. And so actually that will simplify the tan beta. Okay, make sure you're happy with that simplification, right? So tan beta, because sine over cos goes to tan. Okay, so tan beta is going to be, now this looks a bit ugly, right? So if I divide these two expressions, well, what I could say, again, if you're a bit uncomfortable with the dividing fractions, right, like this, we can do it step by step, right? So it's going to be u root 3 over 8 divided by u over 2. Then we do KSC, keep flip change. So we're going to times by 2 over u. And then that will simplify to 2u root 3 over 8u. Well, then the u's cancel. And then that just goes to a quarter root 3. So we just get root 3 over 4. Okay, hopefully happy with that simplification there. Then I can just do inverse tan to get beta to be 23.41 degrees to 2 decimal places, right? And so that's my angle beta there. Okay, so there we are. So hopefully happy with that. But it wanted us to find the angle deflection. So okay, so remember, if I was to continue, let me get rid of this. If I was to continue the original speed like that, And then this will be 60 as well, because remember, we've got vertically opposite angles, okay? So then the angle deflection is going to be this whole angle here, which is going to be beta add 60, right? So the angle deflection is going to be beta add 60, but we know what beta is. That is 23.41 add on the 60, so that'll be 83.41. okay, so that's my angle deflection there, 83.41 degrees, right? So hopefully happy with that, right? So if I just do it in a different color just to really illustrate that, that's my angle deflection there, right? It starts here and ends here. So that's my angle deflection. So it goes 60 degrees and then beta degrees as well. Okay, and so there we are. Okay, and now I've got this question here. So here I'm told a smooth billiard ball strikes a smooth cushion at an angle alpha to the cushion where tan alpha is 3/4. The ball rebounds at an angle beta to the cushion where tan beta is 5/12. So he wants me to find kinetic energy lost. Now, this is sort of a more practical question because it's talking about billiard balls and stuff like that. But really at the core of it, it's literally just another standard collision between like a surface, right, which we looked at previously. So don't get bogged down about what is going on here. And by the way, this is just referring to snooker, by the way. The billiard ball and cushions, basically snooker. That's what's going on a snooker table, right? But anyway, let's not get bogged down about that. So let's just literally draw the scenario. So again, it's just a collision with a surface, a wall or floor, something like that. So let's say it looks like this, right? Okay, so this is my sort of surface here. And then the ball is going to move like this before the collision. And then afterwards, it's going to move, let's say, like that. Okay. So this is my before and after speed u and v. Hopefully happy with this. Okay, now I'm told the angles. Well, firstly, before it hits angle alpha, then afterwards it has an angle beta. Okay, like this. Now we're not told what the angles are exactly, but we're told what tan of it is. Now remember, we looked at examples in previous chapters where we can use tan alpha to find sine and cos. Okay, so firstly, tan alpha is 3/4. Now remember your SOHCAHTOA, right? So we can easily find sine and cos without having to do inverse alpha by using a triangle like this. So I have my angle here, okay, alpha, and then now if we study this fraction for tan, well, remember tan is opposite over adjacent, so the 3 has to be opposite and 4 is adjacent to the angle. And actually, if you do a bit of Pythagoras, then the hypotenuse will be 5, right? So remember, root 3 squared and 4 squared will get be 5. Okay, due to Pythagoras. So now that I've got my hypotenuse, I can work out sine and cos. Okay, so sine alpha, well, sine is opposite over hypotenuse, so it's going to be 3/5, and then cos is going to be adjacent over hypotenuse. So there we are. We got sine and cos. I can do the exact same for the other angle beta. Okay. So beta is here. Now tan beta is 5/12. So again, the opposite is going to be 5 and the adjacent is 12. Okay, and so you can deduce that the hypotenuse is 13. If you do root 12 squared and 5 squared, you will get 13. Okay, due to Pythagoras. But there we are. Now that we got all our lengths, we can also deduce sine and because for this beta, sine beta is going to be 5/13, opposite over hypotenuse, and cos is going to be adjacent over hypotenuse. And there we are. We're going to be needing sine and cos, okay, in the question, because that's going to be to do with the parallel and the perpendicular parts, okay. So there we are. Okay, and speaking about that then, we can split up the two sides like this. Again, as usual, u sine alpha and then u cos alpha. And then this is going to be v cos beta. And then v sine beta here. Now again, firstly, the parallel speeds that are equal. So that means across the surface, that means u cos alpha is going to equal v cos beta. Okay, then perpendicular. Well, the perpendicular parts, that's going to be u sine alpha and v sine beta. So v sine beta is going to be e lots of the original speed, so u sine alpha. Okay, so now that we've got our equations, we can now just simplify them, right, and solve what we need. Now actually, in this particular case, we know what beta and alpha are. We know what cos and sine are, right? We've just derived them, right? So actually, we can simplify two equations quite nicely. So we could say for the first one, u lots of cos alpha, but we know that cos alpha is 4/5. So u lots of 4/5 is going to be v lots of cos beta. Now cos beta is 12/13. Okay, hopefully happy with that. So this simplifies to 12/13v is going to be 4/5u. Then I can divide by 12/13. So I can actually directly easily solve for v here. And so I get 13/15u. Okay, and there we are. That is v there. I can also then do the same for the second equation. So now v, which is now 13/15u, and then sine beta. Now sine beta is 5/13, right? That's going to equal e lots of u sine alpha. Now sine alpha again is 3/5. So there we are. So we can actually solve for e here. So if we simplify all of this, okay, well firstly 13/15u times 5/13 gets me a third u. That's going to equal 3/5 u lots of e. Therefore e, if I just divide by 3/5u, okay, well actually if we work that out, e is just going to be 5/9, and there we are. That's e there. And actually, we've actually done part B before part A actually here. Now part A wants me to work out the fraction of the kinetic energy lost. So we need to consider the loss in kinetic energy. Now remember from chapter 4 when we looked at 1D collisions, the loss in kinetic energy in a collision is the kinetic energy before take away the kinetic energy after. Very standard equation, right? So now we need to work out the kinetic energies before and after. Now, kinetic energy before the collision, well, the speed before the collision is u, right? Is u. And the mass, again, we're not told any masses either, so it's literally just going to be a half mu squared, right? And then the kinetic energy afterwards is going to be a half of mass m, and the speed afterwards is 13/15u. So we're going to square that, and so we can square that, and so this will simplify to 169/450 u squared. No, sorry, mu squared. And so there we are. Okay. So therefore, the loss in kinetic energy is just going to be half mu squared. Take away 169/450 mu squared. Okay. Now I can simplify this. I can factor out a half mu squared. right? So that's going to be 1 take away. Now, if I factor a half out of 169 over 450, I want to do 169 over 450 divided by a half. So that's going to be 169 over 225 after we pulled out a factor of a half, right? That makes sense because if we were to then multiply a half by this fraction here, I should get back 169 over 450, okay? But hopefully happy with that factorization. I can then simplify this even further, okay? And so if I do 1 take away 169 over 225, I get 56 over 225, okay? And that's my answer there. But that's not what they wanted. They wanted me to find the fraction of the kinetic energy lost, okay? So the fraction of the loss in kinetic energy, okay, is going to be, well, it's going to be the loss in kinetic energy over the total energy we originally had, right? So it's going to be the kinetic energy before. Because remember, we lose kinetic energy after a collision. So the energy we had totally before is going to be my my total kinetic energy. And so there we are. So now we're just subbing these values in. Half mu squared of 56 over 225 divided by half mu squared. That's my kinetic energy before the collision. And so actually it simplifies quite nicely because the half mu squareds cancel to get 56 over 225, okay? And there we are. And actually, if you wanted to, you could convert this as a percentage just to really help visualize it, right? So if I times this by 100, you should get 24.89%. So this is telling me how much kinetic energy I've lost as a percentage, right? So I lose roughly 25%. So the kinetic energy I have remaining is 75% thereabouts, right? So it's not the worst collision in the world, right? I still maintain most of my energy, right? But that's what this is. That's what this result is saying, okay? But there we are, okay? And also this makes sense because remember my speed afterwards is 13 over 15 knots of u, so the speed hasn't changed that much, right? It hasn't gone down that much from u to 13 over 15 knots of u, so I don't expect to lose a lot of kinetic energy anyway. But there we are. Now I've got this question here. So here I'm told a small smooth ball is falling vertically. The ball strikes a smooth plane which is inclined at an angle alpha to the horizontal, where tan alpha is a half. Immediately before striking the plane, the ball has speed 5. Coefficient restitution is a half. Find the speed of the ball afterwards. Okay, so it's a slightly different question here. Now the angle it's referring to here, angle alpha, that is not the angle the ball is making, okay? That's the angle of the surface, the plane. So the plane is at an angle, so it is a slope. So it's very, very similar to problems we've seen before in previous chapters, right? Where the surface is at an angle like this, okay? And there we are. So there we are. Now, what I'm told here is we got a ball that is falling vertically. So if I have my ball here, let's say, it's just going to drop straight down like this. It's going to fall vertically downwards, okay? So that's going to be my speed before. Now that the speed before is 5, so it's going to be 5 here. And then afterwards, if you can imagine, after it rebounds off this surface, it's going to look a bit perhaps like this, right? And so that's going to be my after speed v, okay, in that sort of direction there. So hopefully happy with that then. Now, what about the angles? Well, actually, the angles of the speeds. Well, again, we're going to do the same idea of splitting things perpendicular and parallel to the surface. So it's going to look a bit like this, right? So we're going to go downwards and then across the surface like this, okay? And there we are. And then for V, it's going to go across and then up like this, and there we are. So hopefully happy with that. Now, what about the angles? Well, actually, it turns out that this angle here is also alpha. Okay, it's very, very similar to how we resolve weight in this sort of situation. Remember, let's have this situation here where let's have a weight force like this. Remember, we could split up the weight like this, perpendicular and parallel, and this angle is also alpha. Okay, that's because this is going to be 90 degrees, a right angle. This is going to be 90 take away alpha then, okay, due to angles in a triangle adding up to 180. So 180 take away 90, take away 90, take away alpha, gets me 90 take away alpha for that angle there. So that has to force this angle here to be alpha, okay, there. Okay, because obviously then we've got another 90 degree angle. So 90 plus alpha, 90 minus alpha plus alpha gets me 90. Anyway, what you need to know is that this angle, again, very similar to weight, is going to be alpha up here as well. Okay, if I was to, again, do the parallel perpendicular parts, well, this length is going to be 5 cos alpha, because it's adjacent to the angle, and this is going to be 5 sine alpha. Then let's say there's going to be at an angle beta, right? Let's say that's not going to be alpha, by the way. It's going to be a different angle beta. Okay, then this is going to be v cos beta, and then v sine beta here. Okay, very similar to what we did previously with all the examples. So now, if I look parallel to the surface, well, my parallel speeds are going to be 5 sine alpha. That's going to be v cos beta. And then perpendicular. Okay, well, the perpendicular speed, well, it's going to be v sine beta. It's going to be 5 cos alpha times e, right? Because e acts perpendicular. So e lots of 5 cos alpha. My perpendicular speed there. So hopefully happy with that. So now I could just simplify the equations. So therefore v cos beta, well, 5 sine alpha. Now again, we've got the situation where we have tan alpha, not alpha. So I'm going to need to draw a triangle to help me work out sine and cos. So this is alpha, opposite is 1, the adjacent is 2. If we were to do Pythagoras to work out the hypotenuse, you should get root 5. Okay, therefore sine alpha, well, it's going to be opposite over hypotenuse, so it's going to be 1 over root 5, or rationalised to root 5 over 5. And cos alpha is going to be adjacent over hypotenuse, which will go to 2 root 5 over 5. Okay. So hopefully happy with that. So I'm just obtaining my expression for sine and cos there. So therefore, if v cos beta is 5 sine alpha, it's going to be 5 lots of root 5 over 5, right? And so that will simplify to root 5, okay? And that's my first equation. And then if I also then simplify the second one here, well, v sine beta is going to be e. Now, e, we're told, is a half, okay? So it's going to be half lots of 5 cos alpha. Now, cos alpha is 2 root 5 over 5. So if we simplify all of this, we get that v sine beta is going to be root 5 as well. Okay, there we are. So we've got these two equations. Now, they only want me to find the speed of the ball. Okay, So we just need to find v. So I can actually square these two equations to find v. So if I add these squared equations, I'm going to get v squared cos squared beta, and v squared sine squared beta is 5 and 5, right? If you square root 5, and there we are. So that means v squared. Now, what I've done there was, actually I'll do it here. V squared of sine squared beta and cos squared beta is 10. Then I can set this to 1. Okay, this is equal to 1. It's my trig identity, right? So v squared is 10, which means v is just going to be root 10. And there we are. That is my speed there. Okay. Now I've got this question here. So here I'm told a small smooth ball of mass 750 grams falling vertically. The ball strikes a smooth plane inclined at an angle 45. Immediately before striking the plane, the ball is speed 5 root 2. Coefficient restitution is a half, and so it wants me firstly to again find the speed afterwards. So again, it's pretty much the same scenario where the plane or the surface is at an angle. So we've got a situation like this, okay, and it's at an angle 45, okay, and the ball is falling vertically down. So again, it's going to look like this. So it's going to move straight down like this. And the speed is 5 root 2 here. Okay, 5 root 2. Then afterwards, let's say it's going to bounce off like this. I'm going to call that v then, right? Now, if I now resolve the perpendicular and parallel parts, so this is my perpendicular part, then parallel like that. And then for v, again, that is going to go across the surface and upwards like this. Okay, so that's my parallel part and that's my perpendicular part, right? Hopefully happy with that. So now this is going to be 45 as well, right? Okay, actually let me make it a bit clearer. So 45 there. Okay, so that means this side here is going to be 5 root 2 cos 45 because it's adjacent to the angle. And this is going to be 5 root 2 sine 45. Then for the speed afterwards, this is going to be, if I call this beta, let's say, this is going to be v cos beta, and this is going to be v sine beta, okay? Again, make sure you're happy with that, right? The vertical and horizontal parts, the parallel and perpendicular parts, and how I resolved it there. So hopefully happy with all of that. So at this point, again, it's just equations now. So firstly, my parallel part. My parallel part afterwards is v cos beta. So again, that's across the plane, across the surface. Well, that's going to equal 5 root 2 sine 45. That's the parallel part before the collision. Okay, and then perpendicular. Okay, well, the perpendicular parts, well, v sine beta is the perpendicular speed after. Then before, the perpendicular part is 5 root 2 cos 45. But that's going to be multiplied by e, right? Okay, but there we are. So now we just need to simplify, right? And so therefore, v cos beta, well, that's going to be 5 root 2 times sine 45. So we can just put that in the calculator. And we get 5. Okay. And that's my first equation. Then v sine beta is going to be e. Now e is a half. So it's going to be a half times 5 root 2 times cos 45. And so we put all of that in the calculator, we get sine beta to be 5 over 2. Okay. And then I just need to find the speed v. So I can just square both sides. Okay. So if I square both equations and then add them again, that's going to get me v cos squared beta add v squared sine squared beta is 5 squared is 25. And 5 over 2 squared is 25 over 4. So this will simplify to 125 over 4. Okay. So there we are. Well, actually, I can factor out the v squared, and then that'll go to sine squared and cos squared, which is 1. So just v squared is going to be 125 over 4. And so if we root this, we get v to be 5 root 5 over 2. And there we are. And so as a decimal, that will be 5.59 to 3 significant figures. Okay, and that is my speed there. Part B, it says to find the magnitude of the impulse. Okay, now remember, impulse is perpendicular, so the impulse is going to be acting, if I get rid of this, it's going to be acting straight up like this, perpendicular. Okay, so that means impulse again is mv take away mu. Okay, well in this case, I is going to be m lots of the mass. Firstly, the mass. We're told the mass is 750 grams. Now that has to be in kilograms, so that's going to be 0.75 kg. So we need to use standard units here. So that has to go to 0.75 kilograms. Okay. Anyway, so we have impulse to be 0.75 lots of the final speed. Now, because impulse is again perpendicular, we need the perpendicular parts of the speeds. So afterwards, it's going to be v sine beta. Okay. And then we're going to take away the perpendicular speed before, but actually that's going downwards, so it's going to be a double negative, so it's going to be plus 5 root 2 cos 45. Okay, remember it's a negative because it's going in the negative direction downwards. Okay, again the direction of the speeds matters. Okay, anyway, so we're going to get I is 0.75 v sine beta add. Now actually we can work out 5 root 2 cos 45. Put that in a calculator. That's going to get me 5. Okay, so we just need to work out v sine beta. Now we know what v is, right? We might be thinking, well, we need to solve for beta then. We don't really need to, because all I need is just v sine beta. I only need that expression here, but hang on, isn't v sine beta 5 over 2? So I could just sub that in directly without having to work any angles for beta, right? So impulse is just going to be 0.75 of v sine beta, which is 5 over 2 plus 5. Okay. And so that gets me my impulse, if I work all that out, to be 45 over 8. Okay, and that is my impulse there. Okay, so I'm hopefully happy with that. Okay, now we're going to be looking at problems where now we have vectors. Okay, so we can represent the speeds and everything like that in terms of vectors. Okay, and so before we jump into this question, I want to remind you from year 1 corporeal, you should be familiar with the dot product and how to find the angle between two vectors. Okay, so that's the summary there. Okay, we will be using this in the in this question here. Okay, so let's have a look. So here we're told a small smooth ball of mass 2 is moving in the xy plane and collides with a smooth fixed vertical wall which contains the y-axis. The velocity of the ball is minus 6i minus 4j. The coefficient of restitution is a third. Firstly, we need to find the velocity of the ball after the impact. Okay, so the question sounds a bit weird. It's talking about an xy plane, it's talking about a y-axis, but don't get bogged down by that, don't freak out. It's just fluff, really. The main detail really to focus on is that we're told there's a vertical wall. So we've got a wall that's vertical, so it's going to look a bit like that. Okay, so just a vertical line like that. I'm going to call that my wall. Okay, hopefully happy with that. Okay, what I'm also told is the velocity before is minus 6i minus 4j. I'm going to call that u. Okay, so u is going to be minus 6 and minus 4 as a column like this. Hopefully happy with that. And so remember, think back to GCSE or normal maths. What this vector looks like is it's saying we're going to go 6 to the left. So 6 to the left, then 4 down like that. Okay. So my vector overall is going to look like that, and that's going to be what U looks like. So it's going to hit the wall with that sort of vector then. Okay. So that's going to be U. Okay. Then it's going to rebound off the wall. Let's say it looks like that. I'm going to call that V for my velocity afterwards. Hopefully happy with that then, right? So now what I'm going to do, again, like we've done previously, we're just going to now split up into parallel and perpendicular parts. So firstly, U, okay, before, again, we can go down like this and then across like that, okay? Okay, there we are. Then for V, afterwards, again, we can still go down the wall and then across like this, okay? Again, hopefully happy how I've split up the two velocities there, okay? Then I'm going to label my parts. Now, again, as I discussed, for U, it looks like this, right? So we're going to go 6 across and then 4 down like that. Okay. Then V, I'm going to call the parts A and B. So we're going to go A down and then B across like that. Okay. So A and B are my parallel and perpendicular parts there. Hopefully happy with how I split up the velocities like that. Okay. Now, at this point, we are going to consider the parallel and perpendicular parts like we usually do, right? But that we just looked at. So firstly, the parallel parts. Okay. Now, the key thing is, again, because we're dealing with vectors, direction matters. So if we equate the parallel parts, which is 4 and A, again, hopefully you can see they're both parallel, they're along the wall. They're both going downwards. So it's actually going to be A is minus 4. Okay, because A is negative. Okay, because A is going downwards. So A is negative 4. Then perpendicular. Okay, so the perpendicular parts then, that's going to be B is going to be E lots of the original perpendicular part. So it's going to be E times 6. Now B is going to be positive because B is going to the right. Okay, it's going to the right, so it's going in the positive direction. Okay, so B is positive, so it's going to be a third lots of 6. Okay, so that will get me B to be 2. Okay, so hopefully happy with that. Okay, so you need to make sure, this is why it's really helpful to draw a diagram, because it helps you to see what parts are negative and positive, because are they going in the negative direction or the positive direction. Okay, and so then my velocity vector, right, afterwards, well, it's going to be the sort of the X and the Y part. So actually it's going to be BA, okay, because we go across by B and then A there. Okay, so that's going to be 2 for B and minus 4 for A. Okay, so hopefully you are happy with that. Okay, or if you want to do it in terms of I and J, there's going to be 2I minus 4J. And that's my vector there. Okay, hopefully you're happy with that. Okay. So then in part B, it's asking for the kinetic energy lost. So remember, the loss in kinetic energy is going to be the kinetic energy before, take away the kinetic energy after. Okay. So if we work this out individually then, so firstly the kinetic energy before, okay, well, remember kinetic energy is a half mv squared, so half times m, so the mass we're told is, the mass is 2, okay? So it's going to be half times 2 times v squared. Now, we have vectors here for our velocities. So this is my velocity before the collision, right, u. But what we need to do is we need to take the magnitude of u, okay, and then square it. That's what we want, okay? If it's a velocity, we need to take the magnitude and then square it like that, okay? So actually, half times 2 goes to 1, so it's just going to be magnitude of u squared. Now, remember, you should remember how to calculate the magnitude of a vector from normal maths. So in this case, u is minus 6 minus 4, so it's going to be minus 6 minus 4. So that's going to be the root of minus 6 squared and minus 4 squared. But then we need to square that, okay? So the magnitude squared, if we put all that in the calculator then, okay? That's going to be 52, okay? So that's my kinetic energy beforehand, okay? Then I can similarly work out the kinetic energy afterwards, right? So again, that's going to be half mv squared. Well, it's going to be half times 2 for the mass. And now the velocity afterwards is this v, right? So it's going to be v, which is 2 minus 4. So it's going to be the magnitude of v squared. Well, again, that just goes to magnitude of v squared. But v was 2 minus 4. So we need to find the magnitude of that and square it, okay? Again, then that's then going to be the root of 2 squared add minus 4 squared. And then we need to square that, which is 20 joules. Okay, therefore my loss in kinetic energy overall, that's going to be the kinetic energy before, which is 52, take away afterwards of 20, so I get 32 joules of kinetic energy lost there. Okay, and for part C now, it's asking for the angle deflection of the ball. Now, if I just redraw this diagram right here, okay, if I redraw it to help you see clearly what the angle deflection is going to be. So this is my wall, right? So initially the vector was u, which looked like this. And then we had v like that, right? Now the angle deflection, again, if I was to extend and continue on the original vector, the original velocity like this, okay, well, as we discussed previously, the angle deflection is how much I've changed the direction by the angle at which I change. So it's going to be, again, this whole angle here. That's going to be my angle of deflection, right? Now, to work that out previously, what we did was we found the two angles of each vector, right? Individually, we found like alpha and beta, and then we saw that it was alpha plus beta, right? We don't need to actually do that with vectors, because if I just redraw this part out, okay, so I have u coming like this, and then v going like that, and then this is my angle deflection, right? Hopefully happy with that. I've just extracted that part of the diagram. This is my angle of deflection theta. Well, hang on, what we've got here is two vectors and then an angle in between. Well, we need to work out the angle between vectors u and v, but we know how to do that from corpuscle, right? We know that the angle between two vectors is cos theta is the u dot v over the magnitude of u and the magnitude of v, like that, okay? You should be familiar with that formula and how to calculate angles between vectors from corpuscle, okay? And so there we are. Again, remember, the recap is here, okay? So you should be familiar with this from year 1 corpuscle. So we can use the information here to work out the angle deflection. And so really we're just going to substitute u and v in now, right? We're going to be using this formula to work out theta, the angle deflection. So again, here u was, if I go back, my initial velocity was minus 6 minus 4. And then v afterwards was 2 minus 4, I think. Yes, 2 minus 4. So that's my two velocities. So therefore, if I just calculate the angle between them now, using this formula, well, we're going to do the dot product. So minus 6 minus 4 dotted with 2 minus 4 over the magnitude of both of them, right? And then we just need to simplify and work it out, right? So at that point, we're going to get cos theta to be, then if we do the dot product, remember that's going to be minus 6 lots of 2, add, and then minus 4 lots of minus 4, all over the magnitude of both of these. So minus 6 squared, add minus 4 squared, times by the root of 2 squared, add minus 4 squared. And so put all of that in a calculator. And you should get root 65 over 65. Okay. And therefore then we're gonna do inverse cos of that. So then we just get theta to be 82.87 degrees to 2 decimal places, and that is my angle of deflection there. Okay. So there we are. So again, it's quite nice in a way with vectors. We don't need to faff about finding different angles to different vectors. We just can use the angle, this formula here, this straightforward formula to work out the angle deflection in one go. Okay, so so there we are. So again, make sure you're comfortable and you're brushed up on your year 1 vectors knowledge there. Okay. Now we've got this question here. So here we're told a small smooth ball of mass 1 is moving in the xy plane and collides with a smooth fixed vertical wall which contains the x-axis. The velocity of the ball before the impact is 3i and 6j. Coefficient restitution is a third. And firstly, we need to find the speed of the ball after the impact. Notice it says speed, not velocity. But we'll come to that. Okay, now again, the first thing is we want to sort of draw a simple diagram, right, as we've been doing so far. Now again, he looks a bit weird. Again, we're told xy plane and the vertical wall is the x-axis. Okay, again, we're told it's a vertical wall, but actually we're told it has the x-axis. So remember, the x-axis is a horizontal line like this. Okay, so actually it's going to look horizontal. Okay, I don't know why it says with a vertical wall then, because it's a horizontal thing, but there we are. Okay, so if it contains the x-axis, it basically looks like the x-axis. So it's a line like, it's a horizontal line like that. Okay, so then the vector before u is 3i and 6j, so 3, 6 like this. So again, if you were to draw that out, that is saying we're going to go 3 to the right and then 6 up. Okay, so 3 up, 3 to the right and 6 up. Okay, so my vector u is going to look like that. So actually it's going to hit the wall something like this. Okay, so there we are. And then afterwards it's going to rebound off the wall. It will look something like that. Okay, so that's going to be my vector v there. Okay, so hopefully happy with that. And then we're going to split it into parallel and perpendicular parts. So for u, firstly, we're going to go up like this and then across the wall like that. Okay, then for v, again, we're going to go across like this and down like that. Okay. Okay, so again for u, we go 6 up and then 3 across. Okay, remember it looks a bit like this. Okay, so there we are. So hopefully happy with that. And then for v, again, we're going to call it a and b. So we go across by a and then down by b. Okay, so those are my 2 components there for v. So v is going to be ab. Okay, because we're going to go a to the right and then b down. Okay, so there we are. So then at that point, again, at that point, it's quite simple. We're just going to consider the parallel and perpendicular parts. So firstly, the parallel parts are equal. So 3 has to equal A, okay? And A is going to be positive because it's going forwards, right to the right, okay? So that's positive. Then perpendicular. Well, the perpendicular parts, well, B, okay? Well, actually, B is going to be negative because B is going down, isn't it? It's going downwards, which is negative. So it's going to be negative E lots of 6. Okay, that's my perpendicular part before. So hopefully happy with that. So it's negative because B is going downwards in the negative direction. And then we need to multiply by E lots of 6. Okay. And so it's going to be minus E, which was a third. So it's going to be a third times 6, which is going to be minus 2. And so there we are. So that means my velocity vector, AB, will go to 3 minus 2. And that's my velocity afterwards there. But remember, they said to find the speed after, not the velocity. So if we got the velocity then, so again, if so V is 3 minus 2. Therefore, the speed is going to be the magnitude, isn't it? And that's going to be 3 squared add minus 2 squared and then rooted. Okay. So if we just chuck that in the calculator, we get root 13. Okay. So that is my speed afterwards. Okay. Now that follows quite nicely because part B again is asking for the kinetic energy lost. Okay. So the loss in kinetic energy again is going to be the kinetic energy before, take away the kinetic energy after. Well, the kinetic energy before is going to be half times the mass, which was 1, times the speed before. Well, the velocity before is u is 3/6, so we're going to need to magnitude that. So it's going to be magnitude of u squared, which should be a half times 3/6 magnitude squared. Then that's going to be a half times root 3 squared at 6 squared, and then rooted, and then we square again. Okay, so if we work all that out, we get 45 over 2. Okay, and that's my kinetic energy before. Then the kinetic energy afterwards, again, it's going to be half times the mass, which is 1, times magnitude of v squared, right? Well, actually, we already know what the magnitude of v is, right? Thanks to part A. Magnitude of v is root 13. So it's just going to be root 13 squared. And that will go to 13 over 2 joules. Okay, so hopefully you're happy with that. Therefore, the loss in kinetic energy is just going to be 45 over 2, take away 13 over 2, and that will get me 16 joules there. That's how much kinetic energy I've lost. Okay, now we're going to look at I guess more complicated vector questions where specifically the wall or the surface is now sloped. Okay, so what we've looked at the last 2 questions was when the wall was completely vertical like that or completely horizontal like that. Okay, when it's like this, the question becomes quite nice because when the walls are completely vertical, horizontal, we can easily read off the vectors, the velocity vectors, to easily see where the parallel and perpendicular parts are, and then just read off the vector. Okay, but when the wall becomes sloped like this at an angle, it becomes harder. We can't just read off the vector to work out what the parallel and the perpendicular parts are. So we need to come up with a sort of a more general vector method. Now, we're going to use these 2 equations here, okay? Now, the textbook doesn't really go over this at all. The textbook massively overcomplicates this, and I think a lot of students find it very scary because of this. But honestly, it's so dead simple, just using these two formulas. I'm going to go through some questions now just using this. Okay, now I will say these two formulas represent the parallel and the perpendicular components. So the top one's the parallel part, okay, and the second one is the perpendicular part. However, we're not really going to split things parallel and perpendicular, because as you see when we use the equations, we're just going to use the vectors v and u. Okay, we're not going to split up the vector into parallel and perpendicular parts. We're just going to use the vector as a whole. So actually, in a way, it can be a bit nicer with these sort of questions. But we're going to be using these two equations now. I'm not going to do the derivation in this video for time purposes, but I am going to link a video where I do derive these formulas if you're interested to see where they come from. I'm going to link it in the description and maybe the comments, but it should be tagged in this video somewhere. So you want to see where these equations come from, I'll link the video to it there. Okay, but let's just have a look at some questions. And actually, I'm going to look at the exam questions for this first before we look at the textbook questions. Because quite surprisingly, I find the exam questions are actually easier than the textbook questions, surprisingly. But let's have a look at this then. Okay, now the main thing here is you can see the wall is now sloped. It's not completely vertical, horizontal. So we need to use these equations instead, okay? Now, okay, so we're told, we have this diagram here, and we're told the direction of A to B. Now, A to B is the wall. Okay, so we're told the vector AB, so the vector of the wall, is in the direction I plus j. Okay, so that means we could say that the direction vector for the wall, I'm going to say W then, is I plus j, or in column vector form 1, 1. Okay. So hopefully happy with that. So this W is sort of my wall vector. So it's the direction vector of the wall. Hopefully happy with that, right? So it's the direction vector of the wall. Right. Then we're told immediately before the impact, the velocity is a to I and 2j. You can see that there. Immediately after the impact, the velocity is v. The coefficient restitution is a third, and we need to find the velocity vector afterwards. Okay. Okay, so hopefully happy with that. So this is my wall vector. Okay, I also know that my initial velocity u is 8, 2. Okay, or 8i and 2j. Okay, and so then the velocity vector afterwards v. Well, that's what I want to work out. Okay, I want to show that v is 4i and 6j, but I want to work out what v is. So I'm just going to give it this vector ab. Okay, so basically I want to find the coefficients a and b to find v. Hopefully happy with that. So w is the direction vector of the wall, which I'm told is I and j, and u and v are just my standard velocity vectors. Okay, hopefully happy up to here. Okay, now before we can go ahead and apply these two equations, then you'll notice the final missing ingredient is the I here. Now that is your impulse. Okay, so remember, impulse is always perpendicular to the wall. Okay, and so you might be thinking then, if they're perpendicular, we can find the impulse by doing I dot w to be 0, right? Remember from corporeal year 1, two vectors are perpendicular, their dot product is 0, right? So you might be thinking, let's just do that, and maybe let's say impulse is just some vector CD, then I can systematically sort of solve equations. I don't need to do that. Okay, I do not need to do that here. Why? Because I don't actually care about what the precise vector for I is. I don't care about the actual impulse vector. Okay, I only care about a vector that's parallel or a multiple of the impulse vector, because look at this. Okay, this equation is quite specific. Notice how v and u are standard, but notice how w and I have these arrows above above them. Okay, so I have I with an arrow and W with an arrow. Now that's not saying it's the unit vector, that's saying it's a direction vector. Okay, so actually for just the impulse on the wall, I don't care about the technical precise vector for it. I just care about a direction vector. Okay, so what that means is, for example, the wall has this vector 1 1. So we could say that W is 1 1, but actually we just care about a direction vector for W. So actually we could also alternatively take W, my vector W, to be 2 2, or we could take it to be 3 3, or we could take it to be 1,000 and 1,000, right? The idea is we just care about a direction vector. All 4 of these vectors here are examples of direction vector. So it's just a vector that's a multiple. Okay, I don't care about what the actual vector for the wall is. I just care about direction vector. So I can take any of these examples here. Okay, any example that's a multiple, which means because we don't care about the precise vector for the impulse or the wall, what we can say is, if we're going to take W to be 1 1, then we can take the impulse vector to be well, what we would do is flip the 2 components, but actually it's 1 1, so it will still go to 1 1. Then we negate one of them. So let's say I do the top one there, and then I can just find an impulse direction. So that's my impulse direction vector, and that would work because if we were to then do the dot product with W, well, actually, that'd be -1 and 1, which is 0. So they're indeed perpendicular. So as long as we get 2 vectors that work, we don't care about if they're technically, that's the actual impulse vector. I just care about finding a direction vector, okay? And if let's do some more examples just to demonstrate. If, let's say, W was 3 2, then we could say the impulse, if we were to flip it, that would be 2 3, and then let's negate one of them. If W was 10 4, then the impulse would be, let's say, -4 10. Okay, hopefully getting the gist, okay? If W was, let's say, I don't know, -50 and -10, then the impulse vector we could take is going to be 10 and -50, right? If you flip it, -10, -50, then we get rid of one of the negatives. So hopefully you get the gist of that, right? So if we have one of the vectors, then we can flip it and then negate one of them to get the other one, and they should be perpendicular, okay? And so there we are. Okay, so hopefully happy with that. So we can so if we've got the wall vector or the impulse vector, we can flip and negate one of the components to get the other one. Okay, so there we are. So I'm just going to take the impulse then, the impulse direction vector, to be -1 1. So actually now we have an impulse direction, a wall vector direction, and we have U, and we want to find V. Now we can substitute everything into these 2 equations here. So hopefully happy with that. So now I'm just going to sub these into the equations. So firstly, we have V dot W is going to be U dot W. Okay. So in our case, V is AB. So AB dotted with W, which we said was 1 1, that's going to equal U, which is 8 2, dotted with 1 1. And so if we work out this dot product, again, remember from core pure U1, you're going to get A plus B is going to be 8 plus 2, and that will go to 10. Okay, that's my first equation. Then the second equation, well, this is now saying V dot I is going to be minus EU dot I. Okay, so that's going to be again AB for V, and then I, well, a direction vector we said was -1 1. Okay, so I'm going to sub that in. That's going to be minus E, which was a third, I believe. The E is a third. Okay, the coefficient of restitution. And that's going to be U, which is again 8 2 dotted with -1 1 for I. Okay, There we are. And so if we were to simplify this, we're going to get minus a plus b is going to be minus a third of minus 8 plus 2. And so we're going to get minus a plus b is going to be minus 2, I believe. No, plus 2. And there we are. So that's my second equation there. So now I'm in a position where I've got simultaneous equations. So now we can solve for a and b. Okay, so we have a plus b is 10. And then minus a plus b is 2. So it's just straightforward at this point, right? So I could add them to get rid of a. So 2b is 12. Therefore b is 6. And so if we sub b back into one of the equations, we're going to get a plus b, which is 6, is 10. Therefore, a has to be 4. Well, therefore, my velocity vector, which is ab, is actually 4, 6. Okay, and there we are. Okay. So hopefully happy with that. So there we are. So hopefully happy in particular that v and u are my velocity vectors. W and I are direction vectors for the wall and the impulse. Okay, they're not. It doesn't have to be the actual vector for them. It just has to be a direction vector. So we could take any multiples that we want. So again, if W was 1, 1, we could also take 2, 2, or we could take 3, 3, or anything like that. And then the impulse, we can then reverse the components and then negate one of them. Okay. Anyway, then there we are. Okay, so V is 4i and 6j. Yep, that's 4i and 6j. So great, we've done it. Okay. So there we are. So really, once you get the hang of it, it's just substituting into equations like that, really. But there we are. Then part B then says stuff on the magnitude of the impulse. Now this really clearly explains the difference. Okay, so it's asking for the impulse. So the actual impulse vector. This was just a direction of the impulse, so it's just one particular direction vector. I want now is asking for the actual impulse. Remember, the actual impulse can be calculated by the formula I is mv take away mu. That will generate the proper impulse vector, right? Right. So let's just use this equation, right? So that means I is going to be m, which the mass is 0.25, okay? So it's going to be 0.25. Lots of v take away u, so the velocity vector v is 4 and 6. Take away u, which is 8 and 2. Then we just simplify. So I is going to be 0.25, lots of 4 take away 8 is minus 4. 6 take away 2 is 4. And then we multiply by 0.25. We get the impulse to just be minus 1, 1. Okay. But that's the vector for it. It wants the magnitude. So remember, the magnitude is the length. Okay. So it's going to be this formula here. So the magnitude of I is going to be the root of it. So root minus 1 squared of 1 squared. That gets you root 2. And that is my magnitude. Okay. And there we are. Okay, then I've got this question here, and it's sort of in reverse to the last question, really. Again, now we've got a slanted wall again, right? But here we're told at the initial and the final velocities, and it wants me to show that AB is parallel to the vector 2i and 3j. So AB again is the wall. So we need to show that the wall is parallel to this, okay? So basically we need to somehow find W. Okay, in this instance. So if I just label everything then, okay, so U in this case is 7, 2. V is going to be 1, 6. So hopefully happy with that, right? So it's just my two velocity vectors here. W, okay, that's what we want to work out. The a direction for the wall vector W is going to be, let's say, AB. Okay. Now, lastly, the impulse vector. Now, I can't do my trick like I did last time, where I could just flip and negate the wall vector W, because I don't know what the wall vector is. Okay, but actually notice I've got my two velocity vectors. I've also got a mass. So hang on, can't I work out impulse in the standard way? Can't I not say that I is mv take away mu? Okay, so I can work out the impulse vector that way. Okay, and so simply if I work this out, I is going to be 0.5 lots of v take away u. So remember, v was 1/6. Take away 7.2 for u, and that's going to be 0.5 lots of 1 take away 7 is -6, 6 take away 2 is 4, and there we are. So then we can multiply by 0.5 to get the impulse to be -3 and 2. Okay, that's my impulse vector there. Okay, and so there we are. So now I've got my impulse of -3, 2. Now, actually, we don't really need to use the equations, actually, because again, now we can use our trick, right? So if we have the impulse vector, and again, we know the impulse is perpendicular to the wall vector, well, then we can do our trick. We can do our trick of flipping the impulse vector. So -3, 2 will flip to 2 -3, and then we can negate one of them, right? So you might think we could do -2 -3. That's perfectly fine. Okay. Or we could get rid of the -3 to go to +3, and hang on, that matches the vector they've got there. However, that wouldn't be sufficient because we kind of did like a rough trick there. It's perfectly legit. It will give me a direction vector, right? That's what I care about. I want to find a direction vector to show it's parallel. But I need to show it's parallel. So what I need to do more formally now is to take the dot product, and that should confirm they're perpendicular. Okay. And so w dot I, well, that's going to be 2, 3 dotted with -3, 2. Okay. And so in that case, that's going to be 2 lots of -3, add 3 lots of 2. That will get me -6, add 6, which indeed is 0. Okay. So therefore, W must be in the direction of 2, 3, as it's perpendicular to the impulse. And there we are. Okay, so you need to add that justification there. Okay, because it's a show that, right? So there we are. Now, suppose that you took W to be instead -2 -3, because obviously, again, if the impulse is -3, 2, then remember we said that you could take the wall vector to be flipped, so it'd be 2 -3, and then you negate one of them. So in the first example, we negated the -3 to be +3, right? But let's say you minus both of them instead, right? So you negated the 2. That's still perfectly fine. So again, if you did the dot product, okay, you should get 6 - 6, which is still 0. So the dot product works, okay? So it's still perpendicular. So again, because they're perpendicular, W is in the direction of -2 -3. So that means that if it's in the direction, then it just has to be any multiple of this. So it could be -1 lots of 2, 3. So therefore 2, 3 is also parallel to the wall. Okay, so you could justify it that way if you instead negated the other component as well. Okay, but there we are. And then it says in part B to find the value of E. Okay, well actually, now if we look at our equations, can't we just use the second one with E? Because we know what V, I and U are, don't we? So it's just a very straightforward application of this equation here. So I'm going to say that v dot I is minus eu dot I. So in this case, v was 1/6. So therefore 1/6 dotted with I, which was minus 3/2. Is going to be minus e lots of u. Now the vector u was 7/2. Okay, dotted with I, which is minus 3/2. So we just need to calculate these dot products. So 1 lots of minus 3 add 6 lots of 2 is minus e lots of. That's 7 times minus 3, add 2 lots of 2. Again, make sure you're happy with the dot product there. And so simplifying this gets me minus 3, add 12 is minus e lots of minus 21, add 4. Therefore, that will get to that will go to minus e lots of minus 17 is 9. So that means e is going to be 9 over 17. And there we are. That's my coefficient of restitution there. Cool. Okay, so we've got this question here then. So here we're told a small smooth ball of mass 500 grams moving in the xy plane collides with a vertical wall which contains the line x plus y is 3. The velocity of the ball beforehand is minus 4i minus 2j. Coefficient restitution is 1/2. We need to find the velocity afterwards. Okay, so again, if I label my information, u is minus 4 minus 2. Hopefully happy with that, right? Now, what we're told is really funky. We're told the wall, the surface, is in the line x plus y is 3. Now, to kind of visualize that again, kind of convert that into sort of Cartesian form. So if x plus y is 3, therefore that means y is going to be minus x plus 3. Now, what that's going to look like, again, if you sort of do it is some sort of graph, right? It's going to be y's minus x, right? So it's going to look like that, and then I'm going to shift it up by 3. So actually, that's what the direction the wall's going to look like. Again, it's quite funky, but if they give anything in Cartesian form like this, just kind of basically work in sort of the Cartesian form to visualize what it'll look like. But there we are. Okay. Hopefully happy with that. So this is y is minus x plus 3. That's sort of the direction of the wall in Cartesian form. So that's my wall. And so if I now go back to u, so hopefully happy with that, right? It's really, really weird how they give it in Cartesian form, but that's how you can visualize what the wall looks like there. Now, if I go back to u, okay, so minus 4 minus 2, that's telling me I'm going to go 4 to the left and then 2 down. So it's going to look like, that's what u is going to look like. So it's going to hit the wall like that, okay? Hopefully happy with that, right? So there we are. Which means that the velocity afterwards is going to probably look like this as it rebounds, okay? So if I want to work that out, I'm just going to call v to be ab. Okay, so hopefully happy with all of this. Now, I can't work out an impulse vector because I don't know what the final vector is, right? And so I can't work out any impulse vectors at the moment. So I'm going to have to work out somehow a wall vector, so a direction vector for the wall. And again, I'm not given an explicit vector for the wall, but I am told the Cartesian equation. Okay, it makes things a bit more awkward, but actually it's fairly straightforward because if we have the Cartesian equation, again, if we was to if we just look at the equation, again, it's y is mx plus c. We can read off that the gradient is minus 1. Well, actually, the direction vector is basically the gradient. So what that's telling me is if the gradient is minus 1 for the wall, And so then the wall vector then, a direction vector for the wall we can take then, okay, where the gradient is -1, that tells me how y changes when x changes, right? So the directions of x and y. So if the gradient's -1, then let's say if x is 1, then y would change by -1, right? And there we are, okay? Alternatively, we could say, well, let's say if x is 10, then y would change by -10, right? And so again, you can scale the direction vector like this. Okay, so there we are. So if we're given a Cartesian equation, we can use the gradient to work out the direction vector like this. Let's say the gradient was 3, so that means when x, let's say, is 1. So if x increases by 1, y triples. So that would be my direction vector there. If the gradient was, let's say, -11, then that is saying when x increases by 1, y goes by -11. So again, that represents the direction, okay, how x and y change. So hopefully happy with that, right? So if you've got the Cartesian equation, use the gradient because that tells me the direction, right? The gradient is the direction. Okay, so I'm going to take my wall vector to be 1 minus 1. Okay, so again, hopefully happy with that, right? Again, it's a bit confusing when they throw in Cartesian, but there we are. Now, because we have the wall vector, we can now also work out an impulse vector using our trick, right? Because it's perpendicular. So we can just flip the wall vector. So 1 minus 1 will flip to -1, 1. And then we can get rid of we can negate one of them. So actually, we can just go to 1, 1 for I. And there we are. And so at that point, then we can just use the equations to work out these two equations here to work out V. Okay, so firstly, remember that the first equation is V dot W is U dot W. So that means AB for V dot 1 minus 1 for W is going to be -4 minus 2 for U, dotted with 1 minus 1. Simplifying this, we get A minus B is -4 plus 2, and that would go to -2, right? -4 add 2 is -2. And that's my first equation there. Then the other equation, okay, remember, is V dot I is minus EU dot I. Okay, so in this case, that's going to be AB for V dotted with I, which we said was 1, 1. It's going to be minus E. Now E, E's a half, okay? So it's going to be a half. Lots of U, which is -4 minus 2, dotted with I, which is 1, 1. Then if we work out the dot products, we get A plus B. It's going to be minus a half, lots of -4 minus 2. So -1/2 times -6 is going to be +3. So therefore A plus B, simplifying this, we get 3. Okay, hopefully happy with that. So again, I've got simultaneous equations now. So I have A plus B is 3 and A minus B is -2. And so then actually I can add the equations, because then I'll get rid of the b's. So 2a equals 3 minus 2 is 1. Therefore a is a half. Okay. Then I can find b by substituting a back in. So let's say if a plus b is 3, therefore a half plus b is 3, which means that b, 3 take away a half, is 5/2. And that is my my A and B. Therefore my velocity vector V is AB, which is a half, and 5/2. And there we are. That is my velocity there. Then for part B, again, it says to find the kinetic energy lost. So the loss in kinetic energy, okay, that's going to be okay, well, kinetic energy before, take away kinetic energy afterwards. Okay, remember, when it's strictly collisions, this is my loss in kinetic energy formula. So in this case, again, I'm going to do it all in one go. So it's going to be a half times the mass. The mass is 500 grams, but we need to get it in standard units. That's 0.5 kg. So 0.5 for the mass, okay? Make sure you're careful with your units. Okay, times by the modulus of the original speed. Now, u was -4 -2. So it's going to be -4 -2, and then that'd be squared. Take away then a half, lots of 0.5, and then the modulus of the speed afterwards we've worked out to be a half, and then 5/2. And that'll be squared. So if we work all this out, well, half times 0.5 is 0.25. So it's going to be 0.25 lots of the root of -4 squared and -2 squared, all squared. Then we're going to take away 0.25 lots of root of a half squared, add 5/2 squared, and that will be all squared. If I can have some room here. Okay, so if we just put all of that in the calculator, then we get we get 27 over 8. Okay. And joules, and there we are. By the way, you actually don't need to type in the square root in your calculator, because I'm square rooting, but then I'm squaring a root. So actually, all I really need to do in this example, in this part here, for example, if I'm rooting 4 squared and 2 squared, if I'm rooting it then squaring it again, all I need to do is just put in 4 squared and 2 squared. Okay, so don't make sure you can cut down on your calculator time, but stuff like that. But that's my answer, right? And so there we are. Okay, and then part C is asking for the angle deflection of the ball. Now again, the angle deflection. Okay, if I extend the initial velocity u like this, like that, well, then it's going to be this whole angle here, isn't it? Okay, that's going to be my angle deflection theta. Okay, so, well, actually, it's just going to be the angle between v and u. Okay, hopefully you can see that right. So there we are, and again, it's in the correct way. If I was to if I just draw out the diagram here, so v and then u goes away like that. This is the angle deflection theta, and you can see I don't need to worry about the directions, because remember both the vectors here are facing away from the angle. That's what we want. Okay, so now we can very easily just apply the standard formula from Corpuscle 1 for the angle between two vectors. I'm going to do that here. So therefore cos theta, that's going to be u dot v over mod u mod v to get the angle between them, right? Now u is -4 -2, and v was a half and 5/2. Then we're going to multiply their magnitudes. Okay, so just simplify all of this. We get -4 lots of a half, -2 lots of 5/2 over the root of -4 squared add -2 squared times by the root of a half squared add 5/2 squared. Okay, and so at that point we just need to potentially put all of this in the calculator. Okay, And so you get cos theta to be minus 0.6139, blah, 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 blah. Okay. Don't worry about the negative. Okay, that's fine. It just tells me that just tells me it's going to be obtuse. Okay, but don't worry about that. So if I do inverse cos, I get my angle deflection theta. If I do inverse cos of that, I get 127.87 degrees, which is indeed obtuse, and that's the angle deflection there. Okay, and actually that makes sense. Actually, if you just look at my diagram here, it does look like an obtuse angle, doesn't it? So that makes sense with geometrically what we've got. But there we are. Okay, so we've got this final vectors question here. So here we're told a small smooth sphere is moving with velocity 6i and 3j. When it hits a smooth wall, it rebounds from the wall with velocity 2i minus 2j. Okay, so we're told both u and v here. Okay, so u is 6, 3, and v is 2 minus 2. Hopefully happy with that. Right, so we need to find E. Now, we are not told a single thing about the wall here. Okay, so actually, do we even need to use these equations? It might be a vertical horizontal wall. Well, it's not. What is the big giveaway here that tells me the wall is slanted? Okay, that it's not vertical horizontal. If it was to be vertical horizontal like this, then one of the components must be equal. Okay, because there must be a parallel component in that case. But actually, stare at my two vectors, u and v. Neither of the I and j components are equal. U, I is 6, v, I is 2. For j, for j, u is 3, and for v, it's minus 2. So none of the components are equal, which means it can't be a vertical horizontal wall. Okay, it can't be completely vertical horizontal. So the components are, but if both components are different, that's a big giveaway that therefore the wall must be slanted. Okay, so we cannot just equate the coefficients in the parallel perpendicular. We have to use these formulae here. That's the big giveaway here. Okay, but there we are. But actually, even if it was vertical horizontal, by the way, we can still use these formulas, right? I'll go over that a little bit at the end of this, but we're going to need to use these formulas because the wall is indeed slanted here. Now, actually, I don't even really need to draw a diagram because it's asking me for the coefficient of restitution. So it's going to involve this equation here. I'm going to need to find I, but I can work out I because I know what u and v are. So quite nicely, I can just work out I by doing mv take away mu. Okay, there we are. Now you'll notice I'm not told a mass here, but that's going to be fine because again, all I care about is the direction vector. I don't care about the actual impulse vector. I just want a multiple of it, a direction. Let's proceed with this, right? So it's going to be m. I can factor an m out, and that'd be v take away u. Okay, so that's going to be m, and then v is 2 minus 2. Take away u, which is 6, 3. Okay, so simplifying that, we're going to get m lots of 2 minus 6 is minus 4. Minus 2 minus 3 is minus 5. And so you can probably spot then that direction vector is going to be minus 4, minus 5. So I'm going to take the direction vector I, and I'm going to represent the direction vector with this arrow here to be minus 4, minus 5. Hopefully happy with that. So that's not going to be the actual impulse vector. That's just going to be a direction vector, which again can be any multiple. Because remember, m is just a multiple. It's a number. It's a scalar. So there we are. So I'm going to take I in this case to be minus 4, minus 5, my direction vector. And so now, if I want to work out my coefficient restitution, I'm just going to use this formula here. So v dot I is going to be minus eu dot I. Therefore, 2 minus 2 for v, dotted with minus 4, minus 5 for I. It's going to be minus e, lots of u, which is 6, 3. Dotted with minus 4, minus 5, if I squeeze it in there. So if we work out the dot products, I'm going to do it down here, okay? So 2 lots of minus 4, minus 2, minus 2 lots of minus 5 is going to be minus e lots of 6 lots of minus 4, add 3 lots of minus 5, okay? And so we simplify this, we're going to get minus 8 plus 10 is going to be minus e lots of minus 24 minus 15. So therefore, minus 24 minus 15 is minus 39. So we're going to get 39e is going to be 2. So therefore, e is going to be 2 over 39. And that's my coefficient of restitution there. Okay. So there we are. So hopefully happy with that. Now, as I said at the start, again, you might be a bit concerned. What if I don't know what the wall looks like? What if it is vertical and I don't need the formula? When can I use the formula? If you want to be sure, you can use the formula for every vectors question, even if it's vertical or horizontal. Doesn't matter. If it was vertical, let's say, like this, we can still work out the wall vector. Because the wall vector, again, the direction, well, there's no I component, so I is 0, and then j, let's say, is 1, okay? So that'd be my wall vector, a direction, right? If it's vertical like that. Hopefully happy with that. It's just like the j-axis. Alternatively, if it's horizontal, then you'll just take the wall vector, the direction, to be, well, it's sort of in the I-axis, the x-axis, so it's going to be 1 for I and then 0, because there's no j part. So there we are. So when it's vertical, horizontal, you can just take the wall vectors to be that sort of direction there. And then you can apply the two formulas in the exact same way. Okay, but there we are. Now we're going to be looking at some more complicated questions where they're going to throw in a bit of harder algebra and a bit of trigonometry, right? But don't be put off. The process is going to be pretty much the same. We're not going to do anything new here, really. The main idea is going to be the same, but let's have a look at this then. And by the way, because of this, we are going to need some Year 2 pure trig identities. So if you haven't seen it already from normal maths, we're going to be using the trig identities from there. And these are from the formula book, okay? But we'll see what we need as we go along, okay? Let's have a look at this question then. So here we're told a sphere slides across a sphere slides across a smooth horizontal plane towards a smooth vertical wall with a speed of 3v and an angle alpha. After striking the wall, the sphere moves at right angles to the original direction of motion with speed v. And firstly, we need to show that tan alpha is 3. Right, it's quite random, right? How on earth do we get to that? Okay, so again, the situation is pretty much the same, right? So we've got a vertical wall, so it's going to be a wall like that, right? Vertical wall. And so before, let's say it strikes the wall like this, and the speed initially is 3v, okay? And we're told it makes an angle alpha, okay? Then let's say it rebounds afterwards, and the speed afterwards is v, there, okay? Now, I can then call that beta, right? That angle there, beta, let's say. Now, before we go any further, let's read the whole question, because that's not everything. They've also told me, after striking the wall, the sphere moves at right angles to the original direction of motion. What is that referring to? It's saying after it hits the wall, it turns by 90 degrees. It turns at a right angle. What exactly is that referring to? Is referring to the angle deflection. So it's saying the angle deflection is 90. Okay, hopefully you can see that there. Okay, so it's talking about how much the sphere changes by. It changes by a right angle, 90. Hopefully happy with that. That's what they like to do. Okay, they like to add a bit of complicated trig by using the angle deflection. But don't be put off by this, because what's the angle deflection? Right, if I was to extend this again, right, and I know this is alpha again because these two angles are vertically opposite. I also know the angle deflection is alpha and beta. This is the angle deflection here, right? So actually, very simply, that means alpha and beta has to be 90. Therefore, beta is just going to be alpha take away 90. So I can express beta in terms of alpha there. So hopefully you're happy with that. So actually that gives me something to work with. Okay, so I can change beta to alpha minus 90. Okay, so hopefully happy with that, right? So they love to include the angle deflection. Okay, but we should hopefully we are comfortable with that, and then we can go from there. Okay, so the angle beta, I should make that a bit clearer actually. So this is going to be 90 take away alpha. Okay. Okay, hopefully you can see that right, but there we are. So that's my angle afterwards, 90 take away alpha. Okay, we are going to need to use that. So, okay. So now let's apply, that's everything in the question now. So now let's do our usual stuff. So if I, again, split up the components, that's going to be 3v sine alpha, sorry. And upwards of 3v sine alpha. Cos alpha. There we are. Okay. Then afterwards, it's going to go up by v. Well, it would be cos beta, but it's going to actually be cos of 90 take away alpha. And then across up here by v lots of sine of 90 minus alpha. Okay. Hopefully happy with this. Okay. So, okay. Let's do our equations then, right? So standard procedure. So parallel components first. We have that parallel wise 3v cos alpha. Well, that's going to have to equal the parallel component afterwards of v cos 90 minus alpha. Okay. Then perpendicular. Okay. Well, perpendicular wise, the component afterwards is v side of 90 minus alpha. That's going to equal e lots of the original component, so e lots of 3v sine alpha. Okay, so these are my two equations, right? These are my two equations there. Now, how on earth from this are we going to get to tan alpha is 3? Okay. Now, you might be thinking, well, to get tan, usually I'll just divide the two equations, right? You can do that, but if you was to divide include the two equations, you'd have e. We don't know what e is, so we're not going to get to tan alpha is just 3 here. We need to get rid of e. So that means actually we can't use the second equation. We can only use the parallel equation. So if I just consider 3v cos alpha to be v cos of 90 minus alpha, okay? Well, actually, this is a angle formula, right? You should see this from year 2 pure maths. We know that the addition formula for cos is this, right? So let's work this out. So cos of 90 take away alpha, again, if we use the formula book, that's going to be cos 90 cos alpha, okay? And then it's going to be plus sine 90 sine alpha, okay? So this is just using the addition formula for cos, right? This looks really unusual to what we've done, but hopefully you can see that that we can apply standard techniques. So we can apply the addition formula for cos that you should have seen from year 2 pure, but if you haven't, that's the formula, right? We can use the standard formula to simplify this expression here. So if we simplify this then, if I do it bit by bit, we can work out cos and sine of 90. Well, cos 90 goes to 0, so it's going to be 0 lots of cos alpha, and sine 90 goes to 1, so it's going to be 1 lots of sine alpha. Well, very nicely, that tells me cos of 90 take away alpha equals sine alpha. It might be familiar with this already. Actually, this is quite a fairly common identity, but you can use double angle to just simplify it like this. Okay, again, they love doing this. They love using this sort of angle of 90 take away alpha. They love doing it because it simplifies quite nicely. Okay, so hopefully you can see, yes, the question's unusual. Hopefully the steps make sense. Okay, they love doing stuff like this, but hopefully you're with me here. Okay, so if cos 90 minus alpha is sine alpha, if I substitute that in here, that means 3v cos alpha is going to be v cos of 90 minus alpha, or v sine alpha, isn't it? Cos 90 minus alpha sine alpha, so there we are. Hopefully happy with this. And so then I can get rid of the v's. So then sine alpha is going to be 3 cos alpha. What can I do now? Remember, the question wants tan alpha. I can divide by cos to both sides. If I do that, I get sine alpha over cos alpha is 3 cos alpha over cos alpha. And then I can reduce it to tan alpha is just 3. And there we are. I've got the equation they wanted. So yeah, you do need to be comfortable with the with trig identities, right? You should have them back in the back of your mind. Then you can simplify equations like this. But there you are. Hopefully the steps do make sense. Okay. But there we are. Now in part B, it's asking for the coefficient restitution. Now the equation that involves restitution is going to be this second equation here. So let's consider that. Hopefully I copied that right. Okay, yeah. Okay, so if I just rearrange for E then, that's going to be V sine of 90 take away alpha over 3V sine alpha. I can cancel the V's, so that means E is going to be sine 90 take away alpha over 3 sine alpha. Okay, well, I'm going to need this. Okay, again, it looks really nasty, right? So I only know what tan alpha is. Okay, well, the first thing I'm going to do is, again, simplify this sine of 90 minus alpha. Okay. So again, I'm going to use my addition formula. So sine of 90 minus alpha, that's going to be using this formula here. Okay. This formula here. Again, hopefully you're familiar with that from pure maths, from normal maths. So if I sub A and B for 90 take away alpha, that's going to be sine 90 cos alpha take away sine alpha cos 90. Then I can evaluate sine and cos of 90. So that's going to be, well, that's going to be 1 lots of cos alpha, because sine 90 is 1, take away sine alpha lots of cos 90, which is 0. So actually quite nicely this just goes to cos alpha. So therefore E goes to cos alpha over 3 sine alpha. Well, hang on a minute, isn't that just then, if I factor a third out, if I factor the 3 out in the denominator, this is a third of cos over sine. And isn't that just a reciprocal of tan? Well, we know what tan alpha is, don't we? It's 3, right? So there we are. So that's going to be a third of 1 over 3. So therefore E is a 9th, and there we are. Okay, so hopefully you sort of get the essence of this. Again, it's quite unusual. Again, hopefully you see at the end of the day, I am doing the same process of getting the parallel and the perpendicular parts, but then I am simplifying my equations by using trigonometry, using trig equations and going from there. Okay, but hopefully the steps make sense there. Okay, and then I've got this question here. Some type of particle P moving in the vertical plane when it collides with a fixed horizontal wall. Immediately before the collision, the angle of the motion of P and the wall is alpha. So the angle before is alpha, basically. After the collision, the angle is now a half alpha. Coefficient restitution is 0.4, so we need to find alpha. So again, at the end of the day, essentially the situation is the same. So we've got a horizontal wall. So there's going to be a wall that's horizontal like this. And so I've got my speeds. So beforehand, let's say it collides like that. And before, not told any speed, so I'm just going to call it u. Okay. Then afterwards, it has speed v. Okay. So I'm not told any speeds, but I am told the angles. So before, the angle is alpha. Then afterwards, the angle is a half alpha. Okay. And there we are, really. That's pretty much all the information we're given. Obviously, E is also 0.4. Okay, I'll make a note of that. Okay. So again, we're just going to resolve the components. So this is going to be U sine alpha. And then U cos alpha. Then that's going to be V cos of a half alpha. And then upwards like this of V sine of a half alpha there. So again, we're going to do our parallel and perpendicular equations. So parallel. So here we'd get V cos of a half alpha for the component afterwards. That's going to equal the component before, which is U cos alpha, right? Then perpendicular. Okay, perpendicular. So that's going to be V sine of a half alpha. And that's going to be E lots of the original component, right? So it's going to be E lots of U sine alpha. And remember, we also know that E is 0.4. So we can sub that in as well. Okay. So this is going to be 0.4 lots of U sine alpha here. Okay, so these are my standard equations. Hopefully happy so far. Okay, now the question wants me to find the value of alpha. So it's wanting me to work out the angle. Now in this case, it probably is a good idea to divide the equations, right? To find the angle. That's what we normally do, because there we are. So if I divide the two equations, so I'm going to do the second one divided by the first one, because sine over cos will go quite nicely to tan, right? That's my standard technique, right? So that means V sine of a half alpha over V cos of a half alpha. Hopefully you can see the simplification there. That's going to be 0.4 U sine alpha over U cos alpha. Okay, and so hopefully you can see with a trig identity these simplify these two fractions, but v's cancel and sine over cos of the angle goes to tan, so tan over half alpha, and then 0.4 u over u where the u's cancel, and then we get 0.4 tan alpha. Hopefully happy with that. This is using the identity that tan is sine over cos. Okay, which hopefully you are comfortable with from normal maths. But there we are. Right. What on earth can we do here? I can't do any more simplification. But hopefully you notice this is a double angle for tan, isn't it? Because I have half of alpha, then I have alpha here, right? To see this clearly, let's say I let if I let x to be a half alpha, then that would mean that tan of a half alpha, tan x, then is going to be 0.4 tan 2x, and hopefully you can very clearly see the double angle formula here. Okay. Now I'm going to divide by the 0.4. So tan of 2x. If I divide both sides by 0.4, that's going to get me 5 over 2 tan x. Okay. So if I now simplify this with the double angle formula, right? Now we aren't. You don't really work with the double angle formula for tan in normal maths, but we are given the addition formula in the formula book. Okay. So we can generate the double angle formula from this, okay, from the formula book. So if I say A and B is X, right? So therefore, actually, I'm going to do it up here, actually. So again, so if tan A plus B then is tan A plus tan B over 1 minus tan A tan B. Okay, that is just quoting the formula book. Okay, therefore we can derive the double angle formula quite quickly. That means tan of 2x then, which is x at x, is going to be tan x plus tan x over 1 minus tan squared x, right? Tan x is tan squared. So we can use this result for tan 2x here. Okay, so therefore if tan 2x, that's going to be what was it again? Tan x plus tan x. Well, actually, that will go to 2 tan x, wouldn't it? Right? So that'd be 2 tan x over 1 minus tan squared x. That's going to equal 5 over 2 tan x. Hopefully happy with that. I'm just using the double angle formula for tan 2x, okay? Which I've done up here. Okay, hopefully happy with that. So at that point, we need to solve for tan, really. Well, the first thing I can do is, well, I can multiply both sides by 1 minus tan squared. So 2 tan x is going to be 5 over 2 tan x. Lots of 1 minus tan squared x. Let me write that a bit neater. And actually, I don't need to expand this because I can just factor a tan x to both sides. If I move the 2 tan x to the other side, so I'm going to get 5 over 2 tan x of 1 minus tan squared x minus 2 tan x to be 0. And so at that point, we're just going to solve like a standard trig equation from year 1 normal maths, okay? So I can factor a tan x out. So then that would be 5 over 2 lots of 1 minus tan squared. Take away 2 equal to 0. Okay, if I simplify the bracket inside, so I'm going to get tan x or 5 over 2 minus 5 over 2 tan squared, take away 2 equal to 0. That simplifies finally to tan x lots of 5 over 2, take away 2 is going to be a half. Take away 5 over 2 tan squared x to be 0, okay? And so that means either tan x is 0 or 5 over 2 tan squared x is equal to a half. Hopefully happy with that. So I'm just simplifying and solving this trig equation, and I set each bracket to 0. Again, this is just solving a trig equation, okay, like in normal maths, okay? So if I just look at the solutions then, so tan x, right? The solutions we're going to get if we do inverse tan, that's going to be 0, okay? 0 degrees. So then if I now look at this equation, so if I just get tan squared, I'm going to do a half divided by 5 over 2, and that's going to get me a fifth, okay? So that means if I root it, I get tan x to be either plus root a fifth or minus root a fifth. Okay, if I plus or minus the root of that, okay? So then if I do inverse tan of these, that means x then, if I do inverse tan of all of these. Firstly, if I do inverse tan of root a fifth, I get 24.1 degrees to 1 decimal place. Or if I solve the other equation for negative root of fifth, I get minus 24.1 degrees, okay? So, there we are. Obviously, there would be more solutions, because remember with tan, I can just take and add. I could take away or add 180. But actually, let's have a look at the question. Because the question told me that alpha is strictly between 0 and 90. If we look at all our solutions, what's the only solution between 0 and 90? Hopefully you can spot it's just going to be this one, isn't it? So out of x is 0, x is 24.1 and minus 24.1. The only valid solution between 0 and 90 is going to be 24.1. Oh no, sorry, alpha. It's not x, it's alpha between 90. But actually it'll work out the same. So that's x, right? So we want alpha. Now remember, a half of alpha is x, right? Where we did the substitution here. So that means a half of alpha is 24.1. Okay. So therefore, if I double it, I just get alpha to be 48.2 degrees to 1 decimal place, and that's my solution for alpha. Again, if you did a substitution here like I did, make sure you solve for alpha, not x, okay? But yes, that solution is still valid because it's still in the range between 0 and 90 for alpha, okay? So there we are. So again, it's quite unusual to see trig here like this, and solving trig equations, but hopefully you should be able to get my parallel and perpendicular equations, which should be quite standard by now, hopefully, and you should be able to solve trig equations, right? So really, it's a bit unusual, but hopefully the steps make sense here, okay? So there we are. Okay, so we've got an exam question then. I must say this exam question was very tough, very unusual. There's not been a question like this before. It's the only one like this, really. But it's good practice, right? Let's have a look at this. So here we're told a particle P of mass m is falling vertically when it strikes a fixed smooth inclined plane, which is inclined at the angle alpha. Before the impact, the speed is u, then afterwards it moves horizontally with speed v. And we need to show the magnitude of the impulse is mu sec alpha. Now, if you're not aware, sec alpha, well, sec of an angle, sec is 1 over cos. So sec alpha is going to be 1 over cos. Again, that's a reciprocal function which you'll see in year 2 normal maths if you haven't already. So it's referring to 1 over cos. Anyway, so let's draw the situation first, okay? So it's saying it's falling vertically, and I'm also told the plane is at an angle alpha. So remember, it's going to look like this, right? So it's at an angle alpha and it's falling vertically, so it's going to fall straight down like that. Again, we've seen problems like that earlier on in the video, so hopefully you are comfortable with this sort of problem here. Now, the speed initially is u, so it's going to go down with speed u, and then we can split things up like this, okay? So it's going to go down like this and across the slope. Now this angle is going to be alpha here, okay? And there we are. Again, it's very similar to how we resolve weight, okay? So this angle here is going to be alpha, which means this component here is going to be u cos alpha because it's adjacent to the angle, and this is going to be u sine alpha because it's opposite the angle, right? Now, what about afterwards? Now, this is the main thing that stumped people up. We're told afterwards it moves horizontally, which means it moves completely. If we can draw a straight line, it's just going to move left and right. So it's going to move flat like that. Okay, it's not going to be at an angle essentially. So it's going to just go straight across like that. Okay. So there we are. So that's going to be the speed v. Okay, because that's the speed afterwards. So hopefully happy with that. That's the key. I think that's the key. That's the main complexity here, is that it moves horizontally. Now, what does that mean? Well, actually, hopefully you can then see if it's going to move horizontally like this. If it's falling vertically before and then it rebounds horizontally, hopefully you can see again it's going to go at a 90-degree angle. Again, it's that stuff about angle deflection. It moves by 90 degrees, pretty much. So there we are. So actually, again, usually we just work out what we will just call this angle beta, right? The angle afterwards. But if we know this angle here, well, actually, we can, we know, again, this is going to be 90 degrees, right? Because this is the perpendicular component, which means it's right angle to the slope. If we know, because we've got a triangle here, if we know this is alpha and this is 90, we therefore know that this angle here is going to be 90 take away alpha, because all three angles have to add up to 180. If we did 180 take away alpha take away 90, that indeed gets me 90 take away alpha for the last angle there. Hopefully happy that this angle is 90 take away alpha. Hopefully happy with me here. Well, actually, also notice this whole angle here is 180 degrees because this is all on a line, which therefore means 90 take away alpha, add the 90-degree angle here, add the angle beta, has to be 180, right? So we can simplify this equation. So that's going to be 180 take away alpha plus beta to be 180. Therefore, beta is indeed just going to be alpha. Okay, so actually we can simplify and say that the angle beta, more specifically, is going to be alpha here. Okay, and there we are. That is the main thing that stumped people up, I'd say. Okay, it's recognising the angle afterwards is also alpha here. Hopefully happy with that then, right? So there we are. And so there we are. So I think we've used everything the question has told me now. So if I now split, if I now consider the components, well, okay, so afterwards it's going to go again, it's going to go down the slope like this. This is going to be and then it's going to go up like this. So the parallel component along the slope afterwards is going to be v cos alpha, and this bit's going to be v sine alpha. Okay, hopefully happy that I'm splitting up the component afterwards. Again, parallel and perpendicular like this. Hopefully happy with all the components I've done here. So at this point, again, I'm just going to do my two equations. So the parallel component here is v cos alpha. That's going to equal the parallel part before, which is u sine alpha. Okay. I can also do the perpendicular part. Okay. So afterwards, the perpendicular part is v sine alpha. Hopefully you can see that right, perpendicular to the slope. That's going to equal e lots of the original perpendicular component. So it's going to be e lots of u cos alpha. Hopefully happy with the equations here. Okay. I'm not told what e is, so I'm just going to leave it as e. So, okay. Right. So it's asking me for impulse, right? So let's consider the impulse then, right? So impulse I again is mv take away mu. Now remember, impulse is going to act. If I get rid of this now, it's going to act like this, right? Perpendicular. So because impulse is perpendicular, again, that's going to mean we need to consider the perpendicular speeds. So that means it's going to be m of v minus u. Okay, so it's going to be m. Now, v, what's the perpendicular speed afterwards? It's v sine alpha, right? And then I'm going to take away the perpendicular speed before. That's going to be u cos alpha, but remember directions matter. It's going downward in the negative direction. So it's going to be minus u cos alpha. So it becomes a double negative. So we get v sine alpha plus u cos alpha. Okay, very tricky, very fiddly algebra here. Okay, a lot of letters going around, but hopefully you're happy with this, right? Hopefully you're with me here. So I can't do anything more here. Now the expression they want is mu sec alpha. Now again, how on earth am I going to get to that? Well, hopefully you notice the key difference between their expression and my one is that my one has a v in, but their expression doesn't have a v in. So I'm going to need to get rid of v. Now, there's no other equation I can do. I can't pluck any more equations out of thin air. So I'm going to have to look at my parallel and perpendicular ones. Now, I want to get rid of v. Now, I can't use the perpendicular equation because it has an e in. I don't know what e is, so I'm going to have to look at this one. Now, I want to get rid of v, so I kind of need to rearrange for v here. So, if I just divide by cos alpha, I get v. So v is going to be u sine alpha over cos alpha, isn't cos alpha? Well, that quite nicely goes to u tan alpha. Okay, and there we are. So I can substitute that in. So v is going to be m lots of u tan alpha sine alpha plus u cos alpha. Okay, and now I got rid of the v. Okay, I got rid of the v now. So let's factor the u out now, right? So it's going to be mu. Now, it probably is a good idea to say tan is sine over cos. So I'm going to get a sine squared alpha over cos alpha plus cos alpha. Okay. Now, again, how am I going to get the final answer? Let's just continue with this, right? So what I can do now is bring the fractions together. So if I get a common denominator, I'm going to get sine squared alpha, and then cos alpha. If I times by cos again, I get cos squared all over cos. Okay. Well, hopefully it's staring at you now. What else can we do here? I have a sine squared and a cos squared. What does that equal? It equals 1. So I is going to be mu over 1 over cos alpha. Well, hang on then. Isn't 1 over cos alpha this definition here, sec? So it's going to be mu sec alpha there. Okay, quite a very nasty question that is. Okay, I'll make a note here that sine squared and cos squared is 1. So that's what I've used here. Okay, so again, make sure you're happy with your trig identities, but there we are. Okay, yeah, very challenging. That is very, very challenging. But there we are. Then we're told the coefficient restitution is E. Well, we've already used that already, right? We've got the perpendicular equation here, right? So we've got that. So we need to show that v squared is u squared lots of this whole expression here. Now, obviously, we can really only use these two equations here. Okay. Okay. What is the giveaway about what we're going to do to these two equations here? Think about how it's kind of solving for v, isn't it? Here, really, it's solving for the speed v. Think normally, what would we do to these two equations to obtain the speed? We would square the equations, wouldn't we? Right? Let's do that. Okay. So I'm gonna rewrite my equations. So v, what was it? V sine alpha was u cos alpha. No, oh, the other way around. V cos alpha is u sine. Okay, my apologies. That's my first equation. And also, I think it was v sine alpha would be eu cos alpha, I believe. Yep. So these are my two equations, right? My parallel and perpendicular. Now, I'm kind of pretty much want to solve for my speed. So I'm going to square them, right? And add them. That's what I would normally do, right? To find my speed. So let's do that. So it's going to be v squared cos squared alpha, add v squared sine squared alpha is going to be u squared sine squared alpha, add e squared u squared cos squared alpha. Hopefully happy with the algebra here. So what I've done is I squared both the equations, then added them together. So v cos alpha squared is v squared cos squared alpha, then v sine alpha goes to v squared sine squared, then u sine alpha goes to u squared sine squared, and eu cos alpha goes to e squared u squared cos squared. Hopefully you're happy with the algebra here, okay? Hopefully you're happy with that. And so at that point, again, let's look at the question. The question, remember, is rearranging for v squared. So let's do just that, right? So let's solve for v. So actually I can factor a v squared out of the left hand side. So v squared of cos squared and sine squared. That's going to equal, I can factor a u squared out of here as well. So u squared of sine squared plus e squared cos squared. And again, notice I can use my trig identity. Sine squared and cos squared is 1. So I therefore get v squared to be u squared lots of sine squared alpha add e squared cos squared. Now you can't use the identity here because remember there's an e squared. Okay, it's not sine squared and cos squared, it's sine squared and e squared cos squared. I cannot use any identities here. And actually, that should be the equation they wanted us to show. Yep, there we are. Great, great. Then part C is now asking for the loss in kinetic energy. Okay, so now we need to work out an expression for the loss in kinetic energy. Okay. So remember, the standard result for loss in kinetic energy is the kinetic energy before, take away the kinetic energy after. So again, if I do this sort of in one go, that's going to be a half times the mass m, lots of u squared, take away a half, lots of m, lots of v squared. So if I sub in u squared and v squared, that's going to be a half mu squared, then a half mv squared. But hang on, don't we know what v squared is from what we just worked out? I could sub that in. So v squared is going to be this u squared sine squared alpha add e squared cos squared alpha. Okay, so if I expand all of this, I get a half mu squared. I can factor a half mu squared out, can't I? So it's just going to be 1 take away this whole sine squared alpha add e squared cos squared alpha. Hopefully happy with the factorisation there. So I pulled out a half mu squared from both terms. So I can simplify this to 1 minus sine squared alpha minus e squared cos squared alpha. Okay. Now, I might be able to simplify this a bit more, but I'm going to look at what the question wants me to get to. Okay. I need to get to this expression here. Now, what is the key difference between what they've got and what I've got? Hopefully you notice there's no sine involved. There's no sine alpha. And so actually, I have the sine alpha here. So I need to get rid of sine. Now, what identity involves sine squared? And actually, if you actually look at this 1 minus, hopefully you remember that, again, the identity is sine squared and cos squared is 1. Okay. And so therefore, if I subtract sine squared to both sides, that's just cos squared, isn't it? So it's 1 minus sine squared. So actually, hopefully you can see that this 1 minus sine squared here just goes to cos squared due to what we've done here, right? I can sub this in. So hopefully happy with that, okay? So therefore, my loss in kinetic energy is just going to be half mu squared lots of cos squared alpha take away e squared cos squared alpha, and then I can further factorize a cos squared out, okay? And so I get 1 take away e squared. I could actually I could factorize that even further because of the difference of 2 squares, but let me have a look. No, that's the form they wanted. Great, so we've done that now, okay? So again, okay, it looks really nasty, but hopefully you can see, especially for part B and C, it's the same sort of stuff, but we're just involving trig identities, right? Again, it can be quite challenging, but hopefully you're with me, right? Then it says in part D, hence find, in terms of mu and E only, the kinetic energy lost. Now, well, this is the expression for the kinetic energy lost, but it wants me to get rid of the cos, okay? There should be no alphas, only mu and E. Now, how am I going to get rid of cos here, okay? If I want to attempt to get rid of cos, well, again, I can't pull up any more equations out of thin air. Right, I can't, so I can only use these 2 equations really, right? Now, what have we done so far? We have squared the both equations. What's the other technique we do? We divide them, don't we? Okay, now part A, we did divide the first equation. Sorry, we rearranged the first equation, sorry, to get V. But we didn't divide the 2 equations, right? Remember, that's what we can also do, right? So, if I call this equation 1 and equation 2, right? So, if I do the second one divided by the first one then, right? Which is what we normally do, right? So, that's going to be V sine alpha over V cos alpha. It's going to be EU cos alpha over U sine alpha, right? So hopefully happy with this. I'm just dividing the second equation by the first one here, and so I get this result. And so again, the V's cancel, and then sine over cos goes to tan, and that'll go to E. Now, cos over sine is the reciprocal of tan, so it's going to be 1 over tan, right? And so then I can cross multiply to get tan squared is E. Okay, so hopefully happy with that. Now, how on earth is that going to get me cos? How on earth? Because I want cos, don't I, to get rid of it. Okay, well, what other identity can we think of that involves tan squared? Well, if we remember from normal maths, we can use this identity here. Well, hang on, this is basically bingo, because if we have tan squared, 1 plus tan squared, because of this identity, goes to sec squared, and sec is 1 over cos. So actually, we can use this identity to get cos. So if I rearrange this then, okay, so remember that 1 plus tan squared is going to be sec squared. Therefore, tan squared, if I rearrange, it's going to be sec squared take away 1. So what I can do is then, so I've got tan squared is E, but I also know if I rearrange the trig identity, tan squared is sec squared minus 1. So that means sec squared minus 1 is E. And so sec squared is E plus 1. And so remember, sec squared is cos. It's 1 over cos. So 1 over cos squared is E plus 1. Then if I times across, I get cos squared lots of e plus 1 is 1. Then I can divide by e plus 1 to get cos squared is 1 over e plus 1. And there we are. That is an expression for cos. Okay, so that will allow me to substitute into the equation to get rid of it. So cos squared is 1 over e plus 1. So that means, well, I have a cos squared here. So this cos squared, remember, is going to be 1 over e plus 1 because of what we just did, right? Here, right? We just deduced that cos squared is 1 over e plus 1. So there we are. We can just substitute that in. So that means my loss in kinetic energy can be further simplified to a half mu squared cos squared, which is 1 over e plus 1. I'll get rid of this now. Lots of 1 minus e squared. Hopefully you're happy with that, right? So I've got rid of the cos squared because I can substitute cos squared for 1 over e plus 1, which is what we just got. Now, this goes to then half mu squared, lots of 1 minus e squared over e plus 1. Now, we can simplify this further because the numerator is a difference of two squares, right? So it's going to be a half mu squared, lots of 1 minus e, 1 plus e over e plus 1. And actually, I can cancel out the common factor, right? They're both e plus 1. So I get the final simplified expression, half mu squared of 1 minus e. And that is the expression for the loss of kinetic energy with just m, u, and e. Okay. Wow, what a question. Very, very tricky. I'd probably say one of the nastiest questions I've ever asked on this spec in past papers. Very, very nasty question. Okay. So yeah, very A-star question, I'd probably say that is. But yeah, very, very challenging. But hopefully you can see at the core of it, it's mainly just using the parallel and the perpendicular equations, and we basically do the same sort of stuff, right? So we might need to divide equations to get tan for the angle, or we might need to square the equations to get the speed v or whatever. So we get the same equations, but then we're going to throw in some trig identities, okay? So you need to be very strong with your trig identities, but there we are, okay? So that's it for now. I'll see you next time.